what I'm looking for here is, I'm trying to avoid ignorance, okay? And so there are four fundamental forces. Centrifugal force is not one of them, but basically I just want you to be at a point where, like if they're doing some news story about how bad American education is, and they get you, you know, on the camera and they go, "Hello, sir, what's your name?"
Connor Thurman.
And who's your physics teacher?
Mr. Murray.
Do you like him?
Of course.
Yeah, of course, right? He's my favorite physics teacher. And then you go, okay, what are the four fundamental forces of physics? And then you'd be like, I don't know, right? Okay, so that's what we're trying to do here is avoid ignorance, since there are four of them. So if you're taking notes, 1, 2, 3, 4, you know, kind of a thing, okay? And the first one is, and I'm starting from weakest, and I'm going to strongest, okay? The first one is gravity. Gravity is the weakest by kind of a lot. I'll show you the extent of this weakness, okay? Like me, gravity is always attractive. Okay, so it is a force, it is very weak, unlike me, you know? Okay, it's a force that acts on all mass, and it acts between all mass. So every atom, every particle that has mass in this stapler, and every particle that has mass in this remote control is actually exerting a gravitational force toward each other, right? So if the Earth were not so darn close, these guys, we place them in deep space, would drift slowly together. However, as it is now, if I drop them, they just fall, right? Because gravity exerted by the Earth is much, much stronger, okay? But anyway, there it is, right? Okay. The next one, and this is the most common force that we experience in our life, is the electromagnetic force, okay? It attracts and repels, so it's a force between charges. Positive charges repel each other, right? Negative charges repel each other. Yes? A positive and a negative will attract each other, and a negative and a positive will attract each other, yes? So on the average, by the way, if you have two galaxies in space, the net electromagnetic force is probably what? Zero, because on the average of this is zero, right? You're attracting, but you're also repelling, right? Okay, or magnets, right? Two North Pole magnets will repel each other, yeah? Okay, and these things are also intertwined in ways that cannot be separated. That's why they're called electric and magnetic, okay? To make a magnet, okay, a permanent magnet like this, I know that the electrons are actually moving, well, okay, the electrons are going clockwise as seen from above. If I look at this, if this is the North Pole, the electrons are actually more going clockwise around the atoms than anti-clockwise, okay? I know that because this is the North Pole, and if they were positive charges moving, they'd be going anti-clockwise, but these are going clockwise, okay? So to make a magnet, you actually get charge moving in a circle, okay? We can make it with a wire and a battery, right? And then if I take this magnet and I move it near a coil of wire, well, electric current will flow. So somehow a moving magnet can generate, a changing magnetic field makes an electric field. Isn't that weird? That's sort of a weird thing, right? So they're intertwined in sort of interesting ways, right? Fairly strong. Right now, by the way, the force you feel, you're sitting on the table, you feel the chair, you feel anything, right? That force is, when I touch the table, that's the electrons in my hand on the outsides of those atoms being repelled by the electrons on the outside of the atoms of the table, yeah? That's what you feel. All contact forces, almost everything in your experience is this electromagnetic force. Now, let me show you how strong this magnet is compared to gravity. It's stronger than gravity, and I'll show you why. Watch. In one corner we have the Earth, and the Earth is exerting a downward force of gravity on this piece of metal. Yes? There it is. That's what pulls it down. The Earth has a mass of about 6 million. Let me see. There we go, kilograms. Yeah? About 6 million kilograms, yeah? That's kind of a lot, isn't it a lot? Yeah, it's a lot, right? Okay, now, this little magnet has a mass of 0.21357. I'm going to say 89. Okay, kilograms. Yes? Are we ready for this? Are you ready? Competition. The Earth is exerting a downward gravitational force. It is pulling this down. This will exert an upward magnetic force. Drum roll, please. And the magnet wins. The magnet wins again. Let's try it again. Magnet wins again. Oh, I know what you're thinking. You're thinking it's not fair because the magnet is right up against it, right? Whereas this thing is not up against the Earth. So I'll put it against the Earth. Drum roll, please. The magnet won again. Let's try it again. There we go. Yeah, it's always going to win. Do you suppose gravity got stronger when I put it that close to the Earth?
Yes. A little.
Yeah, a little bit stronger, but to the extent that a few inches, right, that 30 inches or something like that is not very much compared to 4,000 miles, right, of radius of the Earth, then it's not going to change it much. Okay? So yeah, electromagnetic forces are way stronger than gravitational forces. However, as far as cosmology goes, as far as astrophysics goes, as far as how galaxies orbit each other and how the evolution of the universe, gravity is far more important because it's always attractive. It's like the tortoise and the hare, right? The tortoise always keeps walking toward the finish line. It's always this is always an attractive force. Electromagnetic forces are inconsequential between galaxies, right? And now there were two other forces. Both of these forces act only in the nucleus. They're extremely short-range forces. So unless you shrink yourself down to subatomic size, okay, we'll talk about how small you'd have to get, right? You're not going to experience these. Now, there are two forces. One of them was not very strong. In fact, you might even say it was a weak kind of force. They were both nuclear forces, okay? And the other one was stronger. In fact, you would say it was a strong force, right? And so they appointed a committee to name these two forces because electromagnetic and gravity already had these fancy names, right? Well, a committee procrastinated. They put it off for months and months, and they actually were, when pressed at the last minute, came up with these two names. One of them is the weak nuclear force, and the stronger one is called the strong nuclear force. Okay, it's very hard to remember. Remember, this is how I remember it, okay? The weak one is weaker than the strong one. It's like, okay. I go to New Seasons, and it's St. Patrick's Day, and I'm getting the corned beef, right? And there's large corned beef and small corned beef brisket, right? And somebody asks the meat counter lady for the 111th time today. They ask her, what's the difference between the small brisket and the large brisket? And she says, well, now the large brisket is larger than the small brisket. You know? Okay, so I'm going to hit the right arrow a couple times. You're not going to really ask any deep, meaningful questions because I won't be able to answer them. Okay, the weak nuclear force explains certain decays. If you don't include it in your calculations, especially beta decays, a beta decay is where a nucleus creates from energy an electron and burps it out. It creates the electron from energy, okay? And in the weak nuclear only acts in the nucleus, and I don't know much about it, okay? Strong nuclear force I know considerably more about, okay? The strong nuclear force is actually a pretty important thing. It explains a lot of things that you might have questions about, right? Okay? So, yeah, right. So the strong nuclear force is the force that's being rearranged in a nuclear reaction, right? So whereas per molecule a chemical reaction might be tens of electron volts of energy, that's a type of energy, right? Okay, these things are millions of electron volts. This is an incredible amount of energy. What they do is the strong nuclear is what holds the nucleus together, right? Now, how big is the nucleus of an atom? Compared to the atom itself, how big? If the atom is the size of the Rose Garden Arena,
a marble.
it is like a marble, depending on the atom, right? Okay, it is a marble. It is a golf ball. It's an orange. It's a basketball, maybe in some of the big giant atoms, right? Okay, but it's relatively small compared to the atom itself, right? So let's draw a picture of an atom. An atom. Here's an atom. I've enlarged this somewhat. Okay, that is 10 to the minus 10th meters. Okay, the atom is about that big. The nucleus of the atom is 10 to the minus 15th meters. You cannot draw a picture of an atom. You cannot draw a picture of an atom. If you make the atom an inch wide, to draw a picture